Well, welcome back to this subject on climate change. And what we're going to talk about in today's lecture is the role of the orbit of the Earth in affecting how much sunlight is received. Remember, we talked about the impact of the amount of sunlight as how it determines the Earth's temperature. And one of the really easy ways to see that impact on the Earth's surface temperature from the amount of sunlight received is to look at the difference between winter and summer. And it's the Earth's orbit around the sun that leads to the seasons. And we're going to look at the impact of the tilt of the Earth's axis in terms of how that affects the amount of sun that's received on the Earth, and then how that affects the temperature, as an example of the way that the change in the amount of sunlight received or the change in the energy balance affects the climate. Because people often say, well, we can't predict the weather for a few days ahead, therefore we can't predict the climate. Well, actually, if we can predict the changes in the radiation balance, we can predict the changes in climate. And the difference in climate between summer and winter is just that sort of prediction. The way that radiation balance changes allows us to predict the temperature response of the climate system. So let's look at the seasonal changes in radiation and how they affect the climate. So let's do a little bit of a review first of all. And what we're going to do again is compare the atmosphere and the positions of the Earth, Mars, and Venus. And the first thing we're going to do, remember, is look at how much carbon dioxide. Remember that they had very similar concentrations of carbon dioxide 4 billion years ago when the planets were forming. But now, while Mars has a very high concentration, it's actually got a very thin atmosphere. It's lost most of its atmosphere. It doesn't have much of a greenhouse effect. It's very cold. The Earth has small concentration of carbon dioxide, but it is a very important contribution. Venus has a runaway greenhouse effect with lots of carbon dioxide concentration. The Earth also has a very important greenhouse effect from the water vapor in the atmosphere, but neither Venus nor Mars have much water vapor at all. And now what we're going to look at as well is the role of the orbit and the orientation of the axis of rotation. The Earth goes around its axis once every 24 hours, but orbits around the Sun once per year. And what we're going to look at is that this tilt of the axis of rotation away from the vertical that we can see over here, the Earth's axis of rotation is tilted away from the vertical. And that leads to a change in the amount of sunlight absorbed in the northern hemisphere or in the southern hemisphere, depending on the Earth's orbit around the Sun. So let's look at the difference in seasons. And what we can see is, yes, the Earth's going to orbit around the Earth's axis once per day, but it also orbits all the way around once every year around the Sun. And so when it's in this orientation, the northern hemisphere is oriented closer to the Sun, not closer to the Sun, oriented more directly towards the Sun. So the Sun is more directly overhead in places in the northern hemisphere. And this would be summer in the northern hemisphere. Whereas if we come right over here now, we see that the Sun is more directly overhead in the southern hemisphere. The southern hemisphere is oriented more towards the Sun, and this would be summer in the southern hemisphere. So we're going to look at those seasons and how that orientation affects the amount of sunlight received at the surface of the Earth. Now, the angle of tilt of the axis of rotation is around 23 degrees. And that's very important. So let's look at that. As I said before, in this season here, it's going to be southern hemisphere winter and northern hemisphere summer, because the Earth is tilted so that the Sun is more directly overhead in the summer here in the northern hemisphere, and the southern hemisphere is tilted away from the direction of the sun's beam. Whereas if we come over here, it's now southern hemisphere summer and northern hemisphere winter. Zoomed in picture of the seasons with the sun and the sunlight. And this season is the southern hemisphere summer. You can see the tilt of the axis here. And the southern hemisphere is oriented towards the sun. The south pole is tilted towards the sun. The sun is directly overhead at 23 degrees south. And that's called the Tropic of Capricorn. There's no sunlight being received in the deep Arctic regions. The Arctic is in darkness. So that means these regions are going to be colder because the sunlight is spread out over a wider area. These regions with the sun directly overhead, 23 degrees south, are going to be receiving the most intense sunlight, and even in the polar regions in the southern hemisphere, they will be receiving sunlight. Now if we go to the opposite season, which is going to be the winter season, now the sun is directly overhead at 23 degrees north. What's called the summer solstice in the northern hemisphere at 20th of June. The sun is reaching the Arctic region, but now there's no sunlight in the Antarctic regions, in the polar regions around Antarctica. And we've got colder temperatures in the southern hemisphere because the sunlight is less directly overhead. It's directly overhead in the northern hemisphere, 23 degrees north. It's at a lower angle in the sky and spread out over a larger area. And when the sun is directly overhead at the equator, what are called the equinoxes, the 20th of March and the 20th of September, that's when we have equal amounts of sunlight in the northern and southern hemispheres, but we still have more intense sunlight where the sun is directly overhead in the tropical regions. We can also look at this sun's path at a region which is away from the equator, like in the southern hemisphere. And in the summer season, the sun will be closest to being directly overhead, and in the winter, it's going to be lower in the sky, even in the middle of the day. And we're heading into the winter in July and August, and that's when the sun is going to be less directly overhead. We've got shorter day length and the sun is at a lower angle in the sky, which means the intensity of the sunlight is much less. So both the change in the direction of the sunlight overhead between the early in the day and the middle of the day and between summer and winter affects the intensity of the sunlight. So we can look at the differences between winter and between summer and determine how this is going to affect the intensity of the sunlight. So let's look at summer first of all here in Melbourne, when the sun is closest to being overhead at what's called solar noon, or 12 o'clock. When we've got daylight saving, that's actually 1 o'clock in the afternoon. But let's call it solar noon when the sun's directly overhead, and that will be at an angle of around about 20 degrees or so, a little bit less. And here in winter, when the sun is much lower in the sky, we have the sunlight being spread out over a larger area. So if we look at the direction from the vertical, the sunlight is not quite directly overhead, but it's only 17 degrees away from being directly overhead. And that means that the intensity of the radiation, perpendicular to this solar beam, the intensity of the sunlight is about 1400 watts per square metre, and it's only reduced a little bit at the surface, whereas when we are in winter, the intensity of the radiation is spread out over a much larger area. So the reduction in terms of watts per square metre is about 1.04 square metres that this beam is spread out over in summer, and in winter it's spread out over more than double the area. The area is now spread out over 2.2 square metres. So the intensity of the sunlight is nearly 1400 watts per square metre, and less than half of that in winter. And that has a massive impact in terms of the energy balance, and that's why we have lower temperatures in winter. But there's another influence as well. What this graph shows is the impact of the changes in the Earth's orbit now in terms of the length of the day. We know that the sun rises earlier in summer and sets later in winter. So this shows the times of sunrise and sunset in Melbourne as a function of the day of the year. If you're in the northern hemisphere, it's going to be quite different. But let's look first of all at the time of sunrise. The sun rises early in Melbourne in summer, the start of the year, and rises again early at the end of the year. We can also look at the times of sunset up here, and the sun sets late in the day, and we see that in winter the sun is setting much earlier, around about 5:30 in the evening like now, and then it sets later again at the end of the day. And this one here, this graph, this curve shows the number of hours of daylight. And this also has a major impact on the amount of energy that a surface can receive. We can see that in summer, in January, and also in December, at the longest day on the 20th of December, there's long hours of sunlight, as well as the sun being more directly overhead, so you receive more sunlight over a longer period, and the sun is more intense. Whereas in winter, the sun is lower in the sky and the number of hours of sunlight is even less. Both of those factors change the amount of energy received at the surface of the Earth. So I've already talked about this, but the interesting thing is that here is the period where the shortest day and the sun lowest in the sky, but actually the lowest, the coldest temperature in Melbourne occurs about a month or so later. And here, the longest day, but the hottest temperature is about a month later. And the delay between the hottest day and the largest amount of energy received is here in, late December, early January. The hottest temperature is at the end of January, early in February. And that's because the climate system has a long time, in this case a month or more, to warm up. It takes time to warm up the land, takes time to warm up the oceans, and this time it means that there's a delay between the hottest temperature, the response of the climate system, to the changes in energy. And that happens also in winter, where the coldest temperatures are delayed relative to the smallest amount of radiation. Well, now let's look at maps of the Earth and where this strongest radiation is. On the 20th of December, the sunlight is most intense in the southern hemisphere. We're getting most radiation in the southern hemisphere. On March 20th, the sunlight is equally distributed. The sun is directly over the equator, and we're getting the same day length and the same intensity of radiation all the way from the North Pole to the South Pole. The length of the day is uniform. We go into the northern hemisphere, what's called the summer solstice in the northern hemisphere or the winter solstice in the southern hemisphere. Now there's no sunlight getting into the polar regions. The day length is longer in the northern hemisphere, and the sun is more directly overhead here in Africa. And let's come back to the autumn, the solstice on the 23rd of September. Now we've got the same day length in the northern and southern hemisphere, and the sun being directly overhead on the equator again. And come back to the 20th of December, summer solstice in the southern hemisphere, and now again we have longer duration days, shorter in the southern hemisphere, long duration, shorter duration days in the northern hemisphere. So the combination of all those effects means that we get large changes in absorbed solar radiation due to the tilt of the Earth's axis, because it changes both the intensity of the sunlight and the length of the day. which change the amount of energy absorbed. And yes, the seasons are different when the northern hemisphere is in summer, the southern hemisphere is in winter, and vice versa. In summer, the radiation is distributed over a smaller area, so that means the intensity of the sunlight is stronger, and the day lengths are longer in summer, so you get more energy absorbed. In winter, the sun is lower in the sky and the days are shorter. But we don't get an instantaneous response. The maximum temperature happens delayed, typically by a month or more, due to it taking time to warm up the land and warm up the ocean. And so what we've learned here is that actually we can predict the temperature response, just change associated with the changes in the energy balance, but the response of the system will take time to respond.